All right, so we're going to work through some practice kinetics problems today. The problems are posted to Blackboard under the lecture notes tab if you want to follow along. I'll also bring them up on the screen here real quick for people to see and give me a little time to copy them down on the white pad. All right, so let's go ahead and get started with that. Someone post a question? Oh no, it's just the meeting started. That always throws me. Like when the meeting starts, it pops up in the chat. Okay, it's weird. All right, and we got Cuddy here too. Yay, the 5 gentlemen. All right, so we'll get going on these practice problems. So I'm going to pull up the practice problems on my screen here, just so we can all kind of see what they look like. So the practice problems here, there's 2 of them we're going to go through today. They're very similar to some of your homework problems that you have, so hopefully you'll learn something here that will help you apply to your homework. Namely, there's some tricks with problem number 2 that you kind of need to identify to work through problem number 2. All right, so we'll start with problem number 1, and it looks very similar to your homework problem number 2. All right, so I'll give you a second to copy down if you got some paper in front of you. Oh, sorry about that. And then we'll flip you over to the white pad and we'll do it. All right, so we've got this homogeneous bar that's attached to this device that's accelerating. Okay, a very strange looking car or something, I don't know. And it's kind of held in this 30-degree position. We're told that this device is accelerating to the right 20 I hat meters per second squared. And we want to determine the force on the roller at A. Okay, so a roller, remember, only one reaction force, and the force on the pin at O. All right, so let us get on with it. All right, I'm going to flip you guys over to the white pad here. Why can I not? All right, here we go. All right, I got to pull that picture in really quick. All right, so away we go. Number 1. And here is our picture. Here's our picture. We have given information about this particular piece. All right, so we, why can I not grab? Usually I'm able to like grab the corner and expand this. Oh well. All right, this guy here is 30 kilograms in mass. We're accelerating to the right at 20 I hat meters per second squared. And for some reason, the coordinate system flipped. That's exciting. We're not going to use this coordinate system. We'll use the traditional coordinate system, which is x, y. All right, so we know that acceleration 20 I meters per second. We want to find here the force at the roller at A. So we want to find the force on the roller at A. And we also want to find the force on the pin at O. All right, so it's a kinetic problem. We'll draw ourselves a free body diagram and kinetic diagram. So let's do that. First, free body diagram. And we're going to do it of this kind of rod-looking device here. We've got our center of gravity here. This is point G. At the center of gravity, we will have our weight acting. Let's use red. Red's more exciting. So here's our weight. Someone muted me? Why did someone mute me? Don't mute me. All right. So at point O down here in the bottom, we have our force at O, y direction. We have a force at O in the x direction. And we also have kind of halfway between these two, this point A. And here we have a force that's acting from this roller. And here it is sort of directed in this general fashion. And we can see that what would be this angle here by the geometry of the problem is 60 degrees. So this will help us resolve things into components. And this guy here is the force at A. So remember that if you have a roller, the force that comes from a roller is directly perpendicular to the object. So here we have a roller perpendicular to the object there. Will give us that force at A, which is 60 degrees with the horizontal. All right, we've got to marry this with our kinetic diagram. All right, so here's our object. And what we'll notice about this particular object is that it's translating. So we only have acceleration in the x direction of the center of gravity. And because it's translating, all points have the same acceleration. So I'll make a note here, it's translating. So we have all points same acceleration, and the angular acceleration is 0. So this object translates with the same acceleration as the base. So here we'll just have MAX, where we know the x component of the acceleration is given to us in this problem 20 I hat meters per second squared. All right, so now we move with our analysis. We'll start with the forces. First things first, it's probably easiest to start with the forces in the y direction because we have no acceleration in y. So let's start with forces in the y direction equals mass times acceleration in the y. Well, we know this mass times the acceleration in the y is 0. And then the forces that we have in the y direction will be equal to the weight, obviously. And this is acting downwards, so negative. We have some component of the force at A acting in the y direction, and here this will be plus the force at A multiplied by the sine of the angle 60 degrees to resolve into the sort of y direction. And we also here have our force at O acting. So here plus the force at O, the y direction, all equal to the acceleration on the right-hand side, which is 0. All right. So let's go ahead and plug some numbers in here. So the weight is the mass times gravity. This bar has a mass of 30 kilograms times gravity, 9.81 meters per second squared, plus sine of 60 is fractional, or if you want a decimal here, 0.866. You know, us engineers, we like 3 decimals. That's good enough for us. 0.866 times the force at A. And then this will also be plus FOY equal to 0. All right, so we got 2 unknowns in this equation. We can sort of rearrange things around to just maybe solve for one of these variables. Let's go ahead and rearrange and solve for the force at O in the y direction. You could pick either one. I've done it for FOY in this particular equation. After some math, 294.3 minus 0.866 times the force at A, and the units on this particular equation is newtons. Let's give this guy a label. Let's say that this is equation 1, so we can come back to this guy later. All right, so that's the forces in the y direction. Can do some similar work on the forces in the x direction. So now let's look at some of the forces. X direction equals MAX, take it to the max. All right. So we've got a component of the force at A here in the x direction, so we need to account for that. And here this is FA cosine, 60 degrees in the x direction, plus the force that's occurring at the pin at O, so FOX, crazy like a fox, not to be confused with crazy like Fox News, completely different. This is equal to the mass times the acceleration of this object. All right, so again, the mass of this object, 30 kilograms, and the acceleration, we do have some components in x, so this on the right-hand side will be equal to 30 kilograms times the acceleration to the right is 20 meters per second squared. All right, again, 1 equation, 2 unknowns, so got to manipulate again. So I'll solve for FOX. This will leave me with crazy like a fox equal to 600 minus 1/2 of the force at A newtons. All right, and let's call this equation number 2. All right, so those kind of force equals ma equations, those are relatively easy. Now the third equation we need to enact is our sum of the moments is Ig alpha. Right. So finally, sum of the moments about point G, okay, remember, got to be about point G, is Ig alpha. Okay, since this thing is translating, our alpha is equal to 0. And we'll just be left with kind of the sum of the moments on the left-hand side. All right, well, there's a couple of different ways to approach this sum of the moments. Hopefully we're comfortable if we're taking some of the moments about this center point here at G. We're comfortable with some shortcuts in that if I need to know the contribution of the moment from this force, well, because this force is perpendicular to the position vector that defines that force, okay, so we see this here is a perpendicular angle, the magnitude of the moment generated is just the length between point G and point A multiplied by the force at A. So if you need some refresher on how to calculate moments quickly, maybe kind of go back to your statics notes and see if we can get up on that. All right, so the contribution from that force at A is simply going to be the magnitude of that force multiplied by the length between the two. So here's the magnitude of that force, Fa, which we don't know, times the moment arm from G to A. So I got to revisit my picture to sort of understand what that is. Okay, well, my center of gravity for this particular guy's going to be sort of here in the middle, which is 1,000 millimeters away from point A. So that is 1 meter if I convert to meters on the fly. So my moment arm here is 1 meter. And this is adding a positive moment in this particular orientation. All right, so that's the moment of the force at A about point G. And I also have contributions to the moment from the pin at O, okay? So if I did something like try to determine the contribution of the moment from FOX, okay? Well, the line of action of that particular force is here. So the perpendicular distance between the center of gravity G and that line of action is something like the length of that segment multiplied by the sine of 30 degrees. Okay, so I want to resolve that moment arm into the contribution that is perpendicular to the line of action of the force. So if I look at the contribution of the moment from FOX, I'm going to have a positive contribution. This will be plus FOX multiplied by the moment arm, which again we have to account for with trigonometry. Here's that total length, which is 2 meters, times here the sine of 30 degrees. All right, similar idea for the y direction. Here we have the force in the y direction multiplied by the total length to get to that position, normalized by the appropriate trigonometric angle. Here it's 2 meters multiplied by the cosine of 30 degrees. And this is all equal to my right-hand side, which is 0. All right. So what I'm going to do here, kind of moved up to the side of me. So what I'm going to do here now is I'm going to take what I learned from equation 1 and equation 2. So here I have an expression for FOY. Here I have an expression for FOX from previous. So I can plug those in directly here and here. And I'll end up with only one unknown remaining, which will be the force at A. So let's go ahead and page down a little bit. So FA times 1 meter plus FOX, which we solve for kind of in equation number 1, is going to be 600 minus 1/2 FA times the moment arm. And if I do 2 times sine of 30, I'll get 1 meter plus FOY, which we solved for previously, is 294.3 minus 0.866 FA multiplied by here my moment arm after doing my trig is going to be 1.732 meters. This is all equal to 0. So the only unknown now in this particular equation, FA, which occurs a couple of times. We can simplify this guy down. And you're left with the force at A is going to be, well, let's just kind of write it all up. This will be FA plus 600 minus 1/2 FA plus 294.3. Actually, let's do the math here. This will be 509.7 minus 1.5 FA equal to 0. So we get down here, and you'll find that the magnitude of this force at A is 1,110 newtons. All right, so that's one of our answers. That's the force the roller applies to the bar. All right, 1,110 newtons. All right. So if we want to be real technical about this, this is the magnitude of the force, because we don't really have a vector quantity at this particular portion. It's just sort of the magnitude of that particular force. All right, so we can plug this back into 1 and 2 to determine FOY and FOX. So if you do that, you'll end up with crazy like a fox is equal to 45 newtons. And the force on point O in the y direction, negative 667 newtons. All right. So note that this particular force at A is a long unit vector which is defined by lambda A is cosine 60 I hat plus sine 60 j hat. You put all these things together and you can actually write your force vectors appropriately using information here, as well as the unit vector along point A for the magnitude of the force at A, and you'll come up with the force acting on the pin at O is 555. Sorry, that's for A. Force at O is 45 I hat minus 667 j hat newtons. And the force at A, if we're resolving into x and y, is 555 I hat plus 691. Dyslexia is hard. 961 j hat newtons. All right, how we do with that? Questions? That one's pretty straightforward, a little bit of like angular nonsense. But it doesn't look like any questions. All right, cool. So no questions on that. We'll go to number 2, which is a little trickier, and we got to kind of talk about a couple of things that are happening with problem number 2. So problem number 2 on this example set is similar to problem number 3 on your homework, and that you're going to have to sort of play a little bit of trickery to make your way through the problem. Right. So I will pull up problem number 2 on the camera here, and we'll give you a second to copy it down, and then we'll talk about it. So we've got a uniform bar here. It's held in equilibrium by chords AC and BD. And then suddenly chord AC fails. So you can kind of see that in the picture there on the left-hand side. We want to determine the tension in cable BD and the angular acceleration of the bar immediately after the chord fails. So here's our problem. I'll give you a second to copy. let's get to it. First thing I want to do when talking about this problem, so I want to ask sort of a general question that's sort of tangentially related to this problem. And my question is this: is it possible at any point in time for me to have zero velocity but non-zero acceleration? What do we think about that in the chat? Either linear or angular. Can I have zero velocity but non-zero acceleration? Tricky. Yes, question mark? Sure, question mark? If no gravity was present, says David. All right. So I think this general concept really kind of throws people off for whatever reason. All right. Let's have a just general discussion about maybe like, well, we're engineers. We talk in graphs. All right, let's talk in graphs. So let's say I'm looking at what my angular velocity of some particular object might be. All right, so this is a graph kind of related to my sort of theoretical problem here. And there's some time here on the x-axis. All right, so we can look at what would be angular velocity, omega, and let's look at, in another color, angular acceleration, alpha. So if I'm cruising along at some constant angular velocity, which is omega, here I am cruising along at some constant angular velocity. If my angular velocity is constant, I'll have no acceleration. Hopefully we can sort of understand that because my velocity is not changing, my acceleration is zero. All right, hopefully that's a good general understanding. However, if all of a sudden,
see your pad.
What's that?
You can't see your pad.
What? Sorry about that. Okay, so here's the pad. I'm talking here. All right, so if we have some velocity that is constant, which I've sort of drawn here, angular velocity that means that my angular acceleration is zero. Here's my angular acceleration, equal to zero. However, now if I start decelerating this guy with some constant angular acceleration, let's turn on some constant angular deceleration, which is down here now, then my angular velocity of my piece will begin slowing down. All right, so let's say that it starts slowing down, and it's going to slow down at a constant rate. Here we are. All right, so at some instantaneous snapshot in time, there will be a point where my angular velocity is actually zero, though my angular acceleration is not equal to zero. All right, so why is that important for this problem? Well, because we have that exact situation here. Right when that cord snaps on this particular piece here, just before that cord snapped, I'm kind of standing still. I have zero angular velocity, okay? But right after that cord snaps, this thing will sort of begin to accelerate with this sort of angular fashion, okay? But I haven't really moved yet, but I'm in the process of potentially moving, all right? So this is another general idea where we might have some angular acceleration alpha, but here we have not yet started moving. All right, so that's kind of the general idea here, and this really kind of throws people off or gets people confused about this particular problem, is that we will have some angular acceleration of this block, but the angular velocity at this particular snapshot is zero because we have not really moved yet. We're looking at the time right after that cord has snapped. All right, so let's keep that in mind as we sort of move through this problem. All right, that will come up later. So first things first, just like we do with all these problems, Freebody diagram, kinetic diagram. So let's find, let's talk about what we know. So we have that the mass of this object, AB, is given to us as, I forget what it was, 50 kilograms? 50 kilograms. And we're also told that cord AC snapped. It should be on that TLC documentary, snapped. All right, we want to find the angular acceleration of AB. and the tension in BD right when this occurs. All right, so away we go. Free body diagram. Of my piece. Here I am, center of gravity. I will have my weight acting, and I have tension on this side in what is wire BD. So here we go. TBD, to be determined. What is the force in that wire? To be determined. Notice I didn't draw any tension on this guy on the left-hand side. That's because that guy has just snapped. We're going to assume that that wire is no longer carrying load. Okay, so my free body diagram is pretty simple. I'll make one note here that we did get the dimensions of this as well. So I'm going to put the dimensions in this free body diagram. All right, kinetic diagram. I really don't know much about what's going to happen with the acceleration of the center of gravity of this guy. So for this kinetic diagram, I'm just going to draw generic force or generic kinetic components. So here this is the mass times acceleration y. Here this is mass times acceleration in x. And I also have my angular acceleration. So my angular component, Ig alpha. All right, away I go with my kinetics. Let's see how far we get. All right, first things first, sum of the forces in x. All right, and this, I'll remind you, is specifically done kind of with the whole body, but we've got really thinking about doing this at point G. So what is the acceleration of point G? All right, well, I don't have any forces in the x. This implies that my acceleration in the x direction for this entire thing is 0. All right, so the acceleration in the x direction for point G is 0. And we could also kind of infer that maybe if we did the sum of the forces about what is point B on this object, we would also get that same analysis. So if I also did like sum of the forces x equals max about B, I would have a very similar result, and that the acceleration at point B in the x direction is also 0. Okay, so no matter where I think about like sum of the forces equals mass times acceleration at sort of any point on this body, I'm going to get that the x direction of the acceleration at any particular point on this body is going to be equal to 0. Okay. Actually, that's not quite true because we want to do our analysis at the center of gravity. Apologies for that. Scratch that. Man, didn't have my coffee today. Let's come back to that point. All right. So anyways, we know that this is analysis is valid at the center of gravity. So sum of the forces x, mass times acceleration x at point G. We know that this is true since there's no forces in the x direction. All right, let's continue on. Sum of the forces y direction, may. All right, so again, we'll revisit our free body diagram. We've got a weight and we've got a tension. So here we'll do tension in BD minus the weight of this object equals the mass times the acceleration in the y direction, which here is 50 kilograms times acceleration in y. All right. So tension in BD minus the weight of this object, 50 kilograms times 9.81 meters per second squared, equal to 50 kilograms times the acceleration in y. All right. So I got to rearrange this guy. I've got one equation, two unknowns, so I'll rearrange. And we'll have that. I'll rearrange for acceleration. It'll be clear why I'm doing that a little bit later. The acceleration in y is going to be 0.02 times this tension in BD minus 9.81 here with units of meters per second squared. All right, I'm going to call this equation here equation number 1. So you could kind of look at this and write for yourself at this point then, what is the acceleration of point G? So with this and with this, we can sort of make our expression for what is the acceleration of point G. So that gives an acceleration of point G, which is equal to 0 in the I hat plus 0.02 TBD minus 9.81 J hat, units here, meters per second squared. All right, so this is something that we'll come back to and revisit a little bit later. All right. So here we have an expression, but it's dependent on that tension. We don't quite know what the tension is, so we have to do a little bit of additional information to kind of find what that tension is before we can continue. Luckily, we've got another equation that we can use, which is that the sum of the moments about point G is Ig alpha. All right, well, that's good. Okay, so the sum of moments about point G, if we're looking at this particular free body diagram, remember here, this is point G. The only force that's going to contribute any moment is the tension at this particular location, with a moment arm here that is half of this 3 meters. All right, so the moment that'll contribute, if I kind of follow the right-hand rule, is going to be a positive K hat. So on the left-hand side, we have this tension in B, D, times the moment arm, 1.5 meters, equal to the mass moment of inertia of this object. We're going to treat it as a slender rod. So if you go to your equation sheet and look up the mass moment of inertia for a slender rod about the through axis, that's the z-axis, it's 1/12 ml squared. So this is 1/12 the mass of the object, 50 kilograms, times the length of the object is 3 meters squared. And don't forget to tack on your unknown angular acceleration of this object at this particular portion, alpha, or I'll call it alpha AB, for this particular object of interest. All right. So we could, again, rearrange this. We have one equation, two unknowns, and let's rearrange. And we could rearrange for either variable, but we'll rearrange here for alpha AB in terms of the tension is going to be 0.04 times tension in BD. All right, here with units of radians per second squared. All right, so let's call this equation number 2. So we're kind of stuck. All right, our angular acceleration depends on the tension, and our acceleration from gravity, or our acceleration at point G, depends on tension. So we're a little bit stuck. We need some additional information. Where do we go? Okay, well, this is kind of a tricky portion of the problem, and it'll come back to sort of the discussion I had at the very beginning of this particular problem. All right, I will say that we need some additional information at this point. So we need additional information. So what do we know? All right, well, what do we know? All right, well, if we come back up to this picture, right when this thing snaps, or really any time that this thing is moving, one thing I do know for sure is this point here is not moving. All right, so the acceleration of D definitely equal to 0 no matter what. All right, so maybe I can do something relating the acceleration of point D to the acceleration of point B, and then relate the acceleration of point B back to the acceleration of point G using some tricks. All right, so let's consider doing that. So we know that the acceleration of point D is 0. That's because that guy is stationary. So let's use kinematics to relate the acceleration of D to the acceleration of B, which we can then relate to the acceleration of the center of gravity of our object using our relative acceleration equations. All right, well, kind of a winding road, but let's do it. All right, so let's talk about that tension in the wire BD. So we're going to kind of relate information again here at point D to information at point B. We're going to assume that that wire is kind of taut through the entire procedure, right? So the acceleration then of point B is equal to the acceleration of point D plus alpha of this wire BD crossed with the position vector that locates B from D plus the angular velocity of this wire BD crossed with angular velocity of this wire BD crossed with the position vector that locates B from D. All right. Well, we don't really know the angular acceleration of BD. We don't really know the angular velocity of BD. But as I was kind of mentioning before, we have this situation where the wire at cord AC is just snapped. So kind of at this particular snapshot in time, none of the pieces have any angular velocity, including this particular cord. But the angular acceleration could possibly still be there. All right, this thing is just about to start moving and swaying, but it hasn't quite moved and swayed just at this particular instant. All right, so let's keep that in mind when we're looking at the kinetic or kinematic relationship between D and B. So, as I just mentioned, there is no angular velocity of that particular guy, 0. But we know that there is angular acceleration because that thing is just about to move. Okay, so this guy here, non-zero. And we also know that the acceleration of point D is 0 because that's fixed. So we can sort of whittle this down a little bit and say that the acceleration of point B is equal to alpha BD crossed the position vector locating B from D. Or if we want to write this sort of in components, the angular acceleration of this wire BD, which will occur in k hat, obviously, crossed with the position vector that locates B from D. Well, I don't know what the magnitude of that is, so let's leave that alone, the magnitude of this position vector BD, but I do know that going or arriving at B from D, I'll have to go in the negative j hat. So what can I infer from this particular piece of information? Well, I can infer that the acceleration of point B, after doing my cross product, k cross negative j will give me positive I. I will end up with something like alpha BD multiplied by the magnitude of the length of the rope BD, all in I hat. Or, long story short, the acceleration of point B is whatever that magnitude is, solely in I hat. All right, so that's kind of a mathematical way to show that the acceleration of point B will only be in the I direction. All right, this is useful for us because we can take that piece of information to the analysis of bar AB to complete that analysis. All right, so back to bar AB. All right, so now if we look at bar AB and we relate the accelerations of the 2 points on the object that we care about, we can relate B to G, and we'll say then that the acceleration of G is the acceleration of B plus the angular acceleration of this body now, which is BD, crossed with the position vector that locates G from B, plus the angular velocity of this object crossed with the angular velocity of this object crossed with the position vector that locates G from B. All right, we know these angular velocities are 0 from previous discussion. And we know that this acceleration of point B is only in I hat from this previous discussion. All right. So acceleration of G we have up here. All right. It's discussed previously. So let's write that straight away on the left-hand side. Acceleration of G, this is 0 in the I plus this quantity 0.02 TBD minus 9.81 j hat. This will be equal to the magnitude of the acceleration of b, which is solely in I, plus the angular acceleration of BD, which is in k hat, crossed with the position vector locating g from b, which is negative 1.5 meters in I hat. All right. So units here, obviously, meters per second squared. Here I have the magnitude of the acceleration of b, whatever it is. I don't know what it is, but I know that it's solely in the I direction. Plus here I have k cross I, which will give me positive j, but I have to retain this negative sign. So I will end up with plus a negative 1.5 alpha BD in j. So the final takeaway is I can directly relate information about the acceleration of point G, which is solely in this j hat direction, to the angular acceleration of this piece BD, and not have to worry about sort of what's going on in I hat. All right. But kind of like I said before, or I mentioned before, you can see here that what's going to pull out of this or result from this is that the acceleration of B is going to be, because there's no counterpoint to match this in the I direction, will be 0. All right, I kind of made mention of that at the beginning of this, but we can explicitly see that now. And I can also look at the j hat direction. So I have 0.02 TBD minus 9.81 equal to negative 1.5 alpha BD. All right, so this is like our third relationship based completely on kinematics. All right, so here I'll plug in equation 2, which, as a reminder, is way up here, the relationship between the angular acceleration and the tension in BD. And I'll have 0.02 tension BD minus 9.81 equal to negative 1.5 times 0.04 TBD. Finally, solving for the tension in wire BD, which is going to be 122.6 newtons. This guy back into what will be equation 2 and also equation 1 will give me the full expressions for the acceleration of this bar at G and also the angular acceleration. So alpha BD, after you plug back into equation 2, will be 4.9 radians per second squared, and the acceleration of point G will be negative 7.36 j hat meters per second squared. All right, there's a lot there. It took longer than I thought, so apologies for that. How are we doing? That was a long one. We can't see. Any other comments, questions on this problem? You can just unmute and talk if you want to chat. All right, well, if there's nothing else, thank you for coming. Hope you have a great Easter if you celebrate. Homework number 3 is due on Tuesday. I'll be around office hours on Monday, so see you guys later.